Drill into the floor of the deep ocean, pull up a core of pale, ancient mud, and somewhere down its length, the world changes color. Above the line sits chalk-white stone, packed with the shells of tiny creatures that rain down through the water for ages. Then, inside a few centimeters, those shells simply stop, and the rock bleeds into a streak of rusty red clay. That red band is a crime scene, 56 million years old. Something flooded the air and the oceans with carbon, and it did it fast, and the planet wrote down every consequence in stone. Here is the part that took the sleep out of my nights when I first understood it. This time, we are the something. We are running the same experiment, only faster than the Earth has ever tried it, and the rock already holds the ending. Let me be careful with you because this story gets abused in both directions. Some people wave the ancient record around to argue that the climate has always changed, so relax. Others reach for it to argue that we are doomed already, so why bother? Neither bumper sticker survives contact with the rock. What the rock offers instead is stranger and far more useful. The one honest forecast we own. Not a model, not a projection, but a thing that genuinely happened, with the results still sitting in a drawer in a research lab, waiting for anyone patient enough to slide it open. Before I tell you what it says then, let me show you how to read it. Start with the shells. Those white layers above the red band are built from the skeletons of plankton, animals so small that a single teaspoon of seafloor mud holds thousands of them. As they die, they sink, and across the ages they pile into chalk, the very stuff of white cliffs and old classroom blackboards. For that chalk to form, the water overhead has to stay friendly to carbonate, the mineral the shells are made of. So when a thick band of shells gives way, in the width of a fingernail, to bare red clay, it does not mean the animals quietly moved house. It means the water itself turned hostile and dissolved their bodies before they could even reach the floor. Picture the red band as the chemical burn left by an ocean that briefly went sour. And a sour ocean points hard at a single suspect: carbon. We can name the culprit thanks to a second clue, this one hidden inside the atoms. Carbon comes in slightly different weights, and living things quietly prefer the lighter kind, sieving it out of the air over long ages and locking it away into wood and the buried sludge that slowly becomes coal and oil. Tear all of that open at once, hurl it back into the sky, and you leave behind a signature nothing can fake. A sharp swing toward light carbon, smeared across the very same slice of rock, on every continent and in every ocean basin at the same instant. Geologists handed this swing a name that sounds like a footnote and reads like an alarm. They call it the carbon isotope excursion. Wherever that red dissolution layer surfaces, the isotope swing rides right beside it, in the same thin band, the whole world over. That worldwide match is what proves it was one event and not a string of local accidents. The mud, in other words, is not guessing. It logged the spill, in a handwriting we have only lately learned to read. That same handwriting is forming in the seabed beneath us at this very moment, taking down our spill with the precise indifference it showed the last one. None of this comes up easily, by the way. The cores are hauled from kilometers down by ships that park over a single spot of open ocean for months at a stretch. The mud sliced into meter-long tubes and read grain by grain under lamps in a lab that smells of cold seawater. Somebody, patiently, counts the shells. Somebody notices the exact layer where the counting stops. That unglamorous, almost monkish labor is the whole reason any of what follows is known at all. Underneath the whole business sits a quiet miracle, that the Earth bothers to keep these records at all. Ice keeps them too. Bore down into the sheets of Antarctica, and you haul up air that has not touched the sky in 800,000 years, sealed inside bubbles, each one a tiny captured breath of an ancient atmosphere you can pop open and measure. Trees keep them ring by ring. Cavestone keeps them, drip by patient drip. Without ever intending to, the planet has become the most obsessive archivist that has ever existed, scribbling its own temperature and its own breath into a dozen different inks. Which makes the far past something far better than a rumor. It is a library, and one volume on its shelves gets pulled down more than any other by the people who study this. Hold that 800,000-year ice record up against a reading taken this morning, and the comparison stops being abstract. Through the whole of that frozen archive, Ice Age giving way to warm spell and back again, the carbon in the air swung inside a familiar band and never once broke past a certain ceiling. Our own sky is now smashed clean through that ceiling and kept on climbing, into country the ice has not seen in nearly 1,000,000 years. Lay this morning's reading beside that whole frozen archive, and the line on ours runs clean off the top of any chart the ice ever drew. Yet the ice only reaches back so far. To find the last time the air held a carbon load like ours, you have to abandon the frozen record entirely and go digging in the rock. And the rock takes you to a place the ice could never reach. Its name is the Paleocene-Eocene Thermal Maximum, such a mouthful that almost everyone shortens it to the PETM. Across what counts in geology as a single blink, the Earth let loose a staggering slug of carbon. Estimates climb into the thousands of gigatons, comparable to the whole stockpile of fossil fuel we could realistically burn if we set out to burn the lot of it. Numbers that large stop meaning anything, so try it this way. Enough carbon to reshape the chemistry of every ocean on the planet, poured into a sky that had been stable for ages. Global temperatures rose by roughly 5 to 8 degrees. From inside our cool, ice-capped world, it reads like a different planet entirely. Far up at the top of the planet, the Arctic Ocean warmed to something near a tepid bath, mild enough to swim in without flinching. Palms and the relatives of crocodiles basked at latitudes that now carry tundra and pack ice. Rainforests crept poleward into country it had no business reaching. Animals answered that heat in ways I keep turning over. Right across the fossil record, mammal lineages caught in the warmth began to shrink, a slow tide of dwarfing that rolls clean through the boundary, with certain early horses dwindling toward the size of a house cat before bouncing back once the planet cooled. Beneath the waves, it was not dwarfing but death, the tiniest accountants of the seafloor, single-celled creatures called foraminifera that had quietly kept house in the deep for an age, were culled so hard that their disappearance is one of the cleanest extinction signals in the whole record. Theirs are the missing shells. Their absence is the red band. So there you have the PETM, the closest rehearsal the planet has ever staged for the thing we are doing this century, and the reason a small army of scientists give whole careers to reading mud. Now, why did the ocean turn corrosive in the first place? And why does that matter so much for us? Here's the chemistry, and it is worth a minute, because it is the hinge of the entire story. Throw carbon dioxide into the air, and a portion of it dissolves into seawater, where it turns into a weak acid. The ocean, left to itself, has a brilliant defense against this. It reaches into the seabed and the continents, slowly dissolving rock, and that dissolved rock neutralizes the acid like a vast antacid tablet. The catch is the word slowly. That rock weathering rescue runs on a timescale of many thousands of years. Spill your carbon slowly enough, and the buffer keeps pace, and the water barely flinches. Spill it quicker than the rock can dissolve, and you blow straight past the defense, and the ocean goes acid before its own medicine can arrive. The PETM crossed that line. We are sprinting across it. The shells dissolve not because there is too much carbon in some absolute sense, but because it came too fast for the planet's own slow cure. Up to this point, I will admit, the PETM almost soothes. Because the world did not end. It sweated and reshuffled. It lost a great deal. Then it carried on. And in a few lucky corners, it even flourished. Stop the story here and you wander off thinking the planet swallowed a giant belch of carbon once before and shrugged. So there is no real cause for alarm. I understand the pull of that ending, but one number has been sitting in my back pocket this whole time. And the instant you hear it, the shape of everything tilts. Speed. That is the whole of it. The PETM bled its carbon into the sky across several millennia. We are matching it in something like 1 or 2 centuries. Run the arithmetic, and the gap refuses to keep quiet. By most estimates, we are pumping carbon roughly 10 times faster than the PETM managed at its absolute peak. And the PETM already held the record as the fastest natural carbon release in the whole archive of stone. We're not repeating the deep past. We have taken the most violent carbon event the planet has staged in a very long age and jammed a thumb on the fast-forward button. Everyone fights about how much carbon. The figure that quietly decides the outcome is how fast. Rate, it turns out, is the entire game. And you already understand why from the chemistry. Speed is what overran the ocean's defense, and speed is what overruns the living world's defense too. Imagine two rooms. In the first, the temperature creeps upward over a long, slow week, and everyone inside has time to notice, grumble, and drift toward the door. In the second, the room hits the exact same temperature in 10 seconds flat. Your thermometer reads identically in both. The outcomes could not lie further apart, because in the second room, nobody got the chance to move. A living world survives slow change by easing out of the way. Species slide their ranges toward the poles or up a mountainside, and over many generations they evolve a degree or two of extra tolerance. One reason, and one reason alone, kept the PETM survivable. It crawled. We copied that ancient recipe to the letter, then binned the lone ingredient, slowness, that once made it survivable. A creature in the PETM could have lived out its whole existence and its children's, and 100 generations beyond that, while the carbon crept up by an amount we now match in a few short decades. What took those animals longer than the whole of recorded history, we are doing inside one lifetime. A child born this year may watch, in person, a shift in the planet's chemistry that the rock normally doles out across tens of thousands of patient years. We have not merely sped the experiment up, we have squeezed it down to a length a single human being can stand and witness from start to middle, which is a thing no creature in the entire record was ever forced to do. Now for the colder edge. The PETM is the kind one. It is the case geologists reach for whenever they want an analogy that ends in hope. Worse things sleep in the rock, and carbon held the knife in those too. Wind back further, to roughly 250 million years ago, to the close of the Permian, and you arrive at the nearest this planet has ever drifted to switching itself off. For once, the name the geologists picked is not a mouthful, but a verdict. They call it the Great Dying. It opened underground, in what is now Siberia, where the crust split, lava welled up, not as one mountain, but as a flood, smothering a region the size of a continent, on and off, for hundreds of thousands of years. Yet the lava was never the murderer. The murderer was what it punched through on its way to daylight. Vast buried beds of coal and salt and rock, cooked and blasted skyward as carbon dioxide and methane and fouler things besides. Up went the temperature, by something on the order of 10 degrees. The oceans lost their oxygen and turned acidic. In the dead, airless deep, bacteria bloomed and exhaled hydrogen sulfide, the gas that stinks of rotten eggs, until parts of the sea may have gone faintly purple and breathed poison back at the land. When the rock reopens on the far side of that boundary, the silence is nearly total. Roughly 9 of every 10 species in the ocean have winked out. Most life on land goes down with them, and the forests fall so completely that the layer just above holds almost no coal at all, a barren interval geologists call the coal gap, the unmistakable mark of a planet that briefly quit growing trees. What inherits this emptied world is a stubby, tusked, pig-sized survivor called Lystrosaurus, for a long age one of the commonest animals left upright, plodding across continents that had fallen to it more or less by forfeit. The reefs took the hardest blow of all, vanishing so thoroughly that there is a stretch of rock with no proper reef in it whatsoever, a reef gap millions of years wide. The Earth had run its carbon experiment with the safety dial wrenched clean off, and came within a whisker of sterilizing itself in the process. What clawed its way back afterward did so slowly, and it returned changed. Survivors of a mass extinction are rarely the grand or the specialized. They are the tough and the small and the unfussy, able to eat almost anything and breed almost anywhere. There is a bleak tenderness in that, life refusing to be deleted outright, clinging on by its plainest and hungriest threads. For a long age after that collapse, the world ran thin and strange, dominated by a few hardy generalists picking over the wreckage of a richer time. Only across the slow climb that followed did variety creep back, niche by niche, until something like a full and varied world stood once more. Read that sequence forward, and it carries a warning with teeth. What the rock means by recovery is never a tidy return to what was lost. It is a different world entirely, built by whatever survived, owing nothing to the one it replaced, and indifferent to whatever it buried. I have to halt on that because of what it murmurs to you. It says the catastrophe has a ceiling, and the ceiling sits close to total. Shove carbon fast enough and far enough, and it ceases to be a weather problem or a rough season for the coast. On the hard physical evidence in the stone, it ranks among the handful of forces that have ever come within arm's reach of wiping every complex living thing off this world. We like to file climate under inconvenience. The rock files it under extinction, and the rock has witnessed a great deal more of both than we have. So the planet pulled through both events, the gentle one and the monstrous one. That is the reassurance you always meet at this moment. The Earth is resilient and life finds a way, and neither claim is false. Let me read you the fine print though, because the fine print is precisely where the cruelty has been hiding. Remember the ocean's slow antacid, the dissolving rock that eventually neutralizes the acid and pulls carbon back down? That is how the planet healed, both times, and it is exactly as unhurried as it sounds. Following the PETM, the Earth needed on the order of 150,000 years to scrub that carbon back out of the air and water and settle into its old skin. Following that catastrophe, the ledger refused to balance for far longer, with living reefs and complex forests taking millions of years to return. By many estimates, somewhere between 5 and 10. So yes, the Earth recovers. It has recovered every single time. It just recovers on a clock that shrinks the entire span of written human history. Every empire and cathedral and name you were ever handed in a classroom, down to a single long afternoon. Set, the planet will be fine against the rock, and it curdles. Because the planet being fine and us being fine have never once, on this evidence, meant the same thing. Now, I promised you honesty, and honesty means showing you where this rock ceases being a clean mirror. Because it does, and anyone who flattens the comparison is not playing straight. The world of the PETM was not our world. No vast ice sheets sat parked at the poles, primed to melt and raise the seas, so that particular menace runs on its own terms for us, in some respects more sharply rather than less. Continents rode in other positions. Currents threaded through other channels. Life itself was cut into wholly different pieces. Deep time is an analogy and never a prophecy. And whoever hands you a precise date or a guaranteed body count off a 56-million-year-old rock is selling a certainty the stone does not hold. What the PETM cannot do is tell you the exact fate that finds us. What it does do with total confidence is show what a fast carbon spike does to any living planet in the general case. It heats the world and sours the oceans, then culls whatever cannot move quickly enough and posts the cleanup bill in units of geological time. The specifics stay ours to discover. The direction stopped being in doubt a long while ago. But the differences cut the other way as well. And this is the part that blindsided me when I first went digging. Every last creature caught inside the PETM and the Great Dying entered it blind. None of them knew the carbon was coming, or grasped what it was, or sensed where it led. The plankton dissolving into that red band carried no concept of carbon, and no memory of any earlier disaster. No move available beyond living and dying inside a catastrophe it could not so much as perceive. And there stands the widest gap between them and us. Wider than the speed, wider than the missing ice. We are the first participants in one of these events who can watch it from outside while it runs. We drilled the cores and measured the isotopes ourselves. We can study the last time this happened the way a detective studies an old case file, then look up and recognize our own fingerprints on the fresh one. No deep-sea shell, no Permian reptile, no forest marching into the warming poles ever once got to know its own ending in advance. We do. Search the whole rock record, billions of years deep, and that has never existed before, not even once. Foresight is the genuinely new variable in the experiment, and it happens to be the only one that was ever ours to spend. And here, finally, is the strange asymmetry where a person might put their hope. Nobody can unwarm the world on command or vote the chemistry of the sea back into something gentler. The speed of the spill, though, the one thing that decided every outcome the rock ever recorded, is also the lone variable still sitting inside human hands. It is the single dial that was ever actually ours to turn, which carries us back at the last to that thin red line in the mud. Because we are laying down a line of our own right now, and we are the first to have ever stood over the page and watched the ink go down. 60 million years from now, long after The Last of Us, something may bore into the floor of a future ocean, pull up a core of pale mud, and find a thin, dark line where the shells stop. That line will be this, right now. Every engine, every flight, every cleared forest, pressed flat into a single centimeter of rusty clay. We never got a vote on whether to leave the mark. That ink began drying the day we first learned to burn. The one number not yet set into the stone, the only part of all this the rock has not already recorded, is how thick we let the line grow.